My name is Zach Berta-Thompson. I'm a new professor at the University of Colorado. And it's my pleasure to be up here to sort of follow on Courtney's perfect introduction and zoom in on a few specific systems that I'm personally really excited about, including some that contain habitable zone transiting planets. So the three systems I want to talk to you about today are, two of them you're quite familiar with. The first of those is TRAPPIST-1. This is a tiny nearby M-dwarf with 7 transiting planets around it. The second is Proxima Cen, the closest M-dwarf, and we know it has a habitable zone planet around it. And then the third is LHS 1140. This is a small nearby M-dwarf that we now know has a transiting temperate terrestrial planet orbiting around it. And so this is a relatively new planet. We just announced the paper yesterday. And so I want to walk you through that system a little bit and place it in the context of other planets that we know of so far. But before I begin, I feel like I need to start with this picture of Proxima Cen taken with the Hubble Space Telescope. And besides the optics of that beautiful telescope and diffraction patterns, we can't distinguish this star from a point of light. That's all we can see. It's just one mere point of light to us. However, we can do a lot with a point of light, particularly from an exoplanet perspective. If a planet's orbit is lined up so that it transits that star, we have an opportunity to measure for an individual planet its size, its orbit, its mass, and its atmosphere. And so I love transiting planets. And so I want to tell you about LHS 1140b, one of the newest transiting planets that we know of. This is a paper that was led by Jason Dittman, a postdoc at MIT. And this was announced yesterday, so you may have read it. If you haven't, I'm going to walk you through the story and tell you how we found this planet and why we're excited about it. So we found this planet with the Murph project. Murph is an array, or 2 arrays, containing 16 40-centimeter telescopes, half of them in Arizona, half of them in Chile. And we've been using these telescopes to photometrically monitor nearby small stars, looking for little dips of light of planets passing in front of them. Dave Charbonneau led the project, and we've been observing for close to a decade at this point. And just a note on the name for Murph. We are, of course, observing the smallest hydrogen-burning stars, which are called M-dwarfs. And we are looking for Earth-like planets. And of course, it's a lot of fun. So we call it Murph. All right. So here's the short version of the story of the discovery. In September of 2014, we saw a 0.5% dip in the brightness of the star LHS 1140. One dip. We got excited about this. We continued to monitor that star, and we didn't see another dip. And that was particularly interesting. If this planet were in a very short period orbit, we would have seen additional transits pretty soon. And so the fact that we didn't see one meant maybe we're talking about a longer period orbit here. So we went out and we gathered radial velocities of the system to try to determine the orbital period of the planet by seeing that star wobble back and forth. And so after after collecting about a year of observations with HARPS, we were able to make firm predictions that we think there's a 24.7-day period in this system. And so we could predict that we should have seen additional transits on September 1st, September 25th, and October 20th. We went out, got the telescopes we needed to observe them, and observed them at that time. And so we knew we had a planet around this system. What do those data look like? The observations here are the radial velocities of the star, so how much the star is moving towards us or away from us. And the 5 meter% wobble of this star tells us that the planet that is orbiting around this small star is 6.6 Earth masses. We can also tell from the orbital period, we know how far away the planet is from the star, and we know that the star emits about 0.3% the power that the sun emits. And so that means we can tell how much energy that planet receives from its star. And this planet receives about 40% the energy that Earth receives from the sun. And of course, we found this in the first place by observing transits. So these are 2 transits from the Murph telescopes. And so from that 0.5% transit depth, we know that this planet is 1.4 Earth radii. And so we have both a mass and a radius for this planet. And it seems to be at a pretty cool temperature. So I want to, that's quick story. The thing I really want to do is put this in the context of other planets. And I'm going to start with the planets you're most familiar with, the 8 planets in the solar system. I left Mercury off here, sorry. So up at the top, you can see that Jupiter and Saturn, this is the same plot that Courtney showed of the masses of planets and the radii of planets on the y-axis here. Jupiter and Saturn, we can explain their radii as a sphere of hydrogen, helium gas. Mars, Earth, and Venus, we can explain their radii with a sphere of rock and iron in the ingredients that Courtney described. Uranus and Neptune are, interestingly, in between those. I can add exoplanet measurements on here where we have both a mass and a radius. Oh, wrong button. And you see, so first of all, I had to do one sneaky thing to make this plot. I had to take those systems where there are large uncertainties on the density of the planet, and I weighted the intensity of those points downward so that systems for which we don't have a very precise measurement, those kind of fade into the background. And the overall trends here are more or less what you expect. Jupiter and Saturn, so the massive planets are basically hydrogen, helium gas. Low-mass planets are, for the most part, consistent with a rocky composition. And then there's this fascinating transition in between where there's all sorts of complicated stuff going on. We can also highlight on here LHS 1140b. From that mass measurement from the radial velocities, it actually appears to be a little bit denser than that standard rock-iron curve. So it might be, this could point to a possibility for different compositions of its bulk composition, but we don't know. It'll be interesting as we get more precise measurements to figure out really what the density of this planet is. I guess the real question is, which side of this error bar will this planet fall as we make more precise measurements? And then there are mass measurements of the TRAPPIST-1 planets that come from the transit timing variation method that Courtney described. Some of those measurements are not particularly constraining, and so you can't even see the points on here. But for those planets that do have relatively tight mass constraints, those seem to be relatively low density, lower than the standard rock iron ingredient. And so that might be pointing to some interesting difference there as well. But now I can add an additional panel onto this plot, which is the heat that these planets receive from their star. So 1 here is the 1400 watts per meter squared that Earth receives from the sun. And there are planets that receive 10,000 times as much heat as that. And I've plotted on here a very rough demarcation of a habitable zone, a temperature range where you might imagine that you could have liquid water at the surface of these planets. This is a very complicated concept, and I'm going to defer to my colleague Eomoy Shields, who's going to tell you more in detail about what that actually means. But LHS 1140b and some of the TRAPPIST-1 planets are in that zone. You'll notice on here that I've added a lot more points on the second panel than were on the first panel. This is because there are vastly more planets that we know of than planets for which we have both masses and radii. The black circles on here are planets for which we have a mass. The gray circles are planets for which we don't know the mass. And that is a really important population of planets because that is the population of planets that taught us the statistics of planets in the habitable zone through Courtney's work. However, until this year, we had no potentially habitable planets for which we had measured densities. But now with LHS 1140 and TRAPPIST-1, we have some systems like that. You'll also notice that, of course, the circles here are sized differently. That's because I have scaled the area of a point to be proportional to the transit depth, the fraction of starlight that planet blocks. And the reason that I've done this, why this matters, is that planets that with deeper transits are easier to observe. If you block a larger fraction of your star's light, you can make a more precise measurement of any signal you want for that. And as an example of that, I want to highlight WASP 43b. This is a pretty standard hot Jupiter for which we've been able to study its atmosphere in multiple ways. And so the first of those methods is that we have watched while this planet passes in front of its star, or I guess I should say Laura Kreidberg watched when it passed in front of the star, and she made these measurements of how much light does that planet block as a function of wavelength. And so we can see that the planet blocks more light at these wavelengths, which happen to correspond to absorption features of water. If the planet's atmosphere absorbs more light at a particular wavelength, the planet's going to appear a little bit bigger. It's going to block a larger fraction of its star's light. So we can, by watching these transits, we can infer the transmission spectrum of light transmitted through a planet's atmosphere. We can also watch a half orbit later when this planet goes behind its star, and you see the light that that planet itself was emitting disappears. And from that, you can infer what was the emission spectrum of that planet itself. The thermal, if you look in the infrared, you're seeing the thermal emission of that planet. And again, you can see a nice water absorption feature here in Laura's plot of the emission spectrum. And so these measurements are possible for WASP-43b because it blocks a relatively large fraction of its star's light. This is why most of our observations of the atmospheres of transiting planets are so far limited to large Jupiter-sized planets. But if I come back to our population of planets, and I add on a panel here that indicates the radius of the star that these planets transit, TRAPPIST-1 and LHS 1140b transit very small stars. And so what that means is that even though they are 10 times smaller than WASP-43b, they still block a relatively large fraction of their star's light, making them relatively easy to observe. So we might be able to make these observations of their atmospheres. And so the final panel I need to put on here is, of course, the distance to these systems, just away from us in space. And of course, closer transiting planet systems are easier for us to observe. For the same planet at 10 parsecs versus 100 parsecs, that's the same difference as you need a 25-meter telescope to study that planet's atmosphere, and you need a 250-meter telescope to study that planet's atmosphere. So the distance of these systems really, really matters. And the moment I say distance, you of course say, why haven't you put Proxima Cen on these plots? And I'm with you 100%, but there's this frustrating feature about Proxima Cen b, which is that it probably doesn't transit. We don't know, but it probably doesn't transit. I guess I'll ask David whether or not we know, but I'll ask him later. So frustratingly, if it doesn't transit, we can't measure its radius because we don't know how much starlight the planet blocks. And we also, though we can measure its minimum mass, there's a degeneracy between the actual mass of the planet and the tilt of that orbit relative to the plane of our sky. So this limits what we can say about Proxima Cen b. But nonetheless, we can put it on our comparison plot, and it is at 1.2 parsecs. It's 10 times closer than these other transiting systems. And we know that its minimum mass is just a little bit more than the Earth, but we don't know the radius of this planet. However, in terms of its environment, the heat that it receives and the kind of star that it orbits is very similar to LHS 1140 and TRAPPIST-1. And this is really, really important because all three of these systems are not the sun. These stars are very, very different from the sun. And so if we want to understand Proxima, particularly if it doesn't transit, we're going to need to use observations of other systems where we can study them in more detail to get context for those for that system. And so TRAPPIST-1 and LHS 1140, though they are farther away, I guess the lucky happenstance of their transiting geometry makes them useful laboratories for understanding Proxima and its planets in general. Even though we can only observe these still just as points of light. And in the last minute here, I just want to highlight that in 1930, the planet Pluto in our solar system, sorry, not planet, whatever, was discovered in our solar system as a point of light moving across the sky. And very recently, with the New Horizons launch that ultimately gave us this picture of Pluto taken from behind, that launch, that mission, was informed by 70 years of observations of Pluto as a point of light. The design of this mission relied heavily on things that we learned through many transit-like techniques for Pluto. And so the question that is most present in my mind here at this conference is, what in situ observations of an M-dwarf planet do I want us to have in 70 years? And I don't know the answer to that question right now. But what I do know is that observations of these systems will help us try to figure out what questions we should be asking, and will help us in our quest to visit habitable worlds outside the solar system. So I will leave it there and take any questions of yours. Avi?
So integrating the previous talks, based on what Courtney told us, there should be at least 1.5 planets in Proxima, in addition to Proxima B, right?
Right.
And so, I mean, we can make guesses as to what the orbital period would be, but what are the prospects for finding them, given that we probably don't have a transit?
Around Proxima B, not the mysterious,
Proxima.
not yet seen planets around LHS 1140.
Well, if you can comment on that, that would be awesome.
Okay. Around Proxima, yes, I think it's interesting to continue to be gathering radial velocity observations. Laura's and your work on studying the phase curves of non-transiting planets, I think, is going to be a really powerful technique for thinking about this. And then for LHS 1140, if these planets are coplanar, the fact that the outermost planet transits is wonderful for us, and that means that if these are all lined up, then anything interior to that will transit. And so as we push down to sensitivity of smaller and smaller planets, I would not be particularly surprised if additional planets popped up in the system. Lisa.
Lisa Kaltenegger, Carl Sagan Institute, Cornell. Great talk, Zach, and amazing observations. I think one of the things that is also really lucky so far is that actually those 3 systems that you mentioned have a different UV component from the activity of the star. So it will be harder for us to figure out, that the comparison. However, we have not only a beautiful planets further away from the star, but also beautiful activity change between the host stars. And so I was wondering if you can comment on how this might influence what kind of planets we can actually spot due to the stellar characteristics that will allow us to find smaller things or harder or bigger planets, spots, and so on and so forth. Do you think that actually limits how deep we can go down in terms of planets for these different stars just due to the host star? And do you have a line, or do you happen to know where that is?
I think that, so as Lisa points out, that these stars are individuals, that they have, that in addition to the overall thermal flux that a star delivers to a planet, it's also delivering high energy radiation, it's delivering particles. So some of that wild magnetic activity makes it difficult to find planets, and so that's certainly an issue for these 3 different systems and the methods we use to find planets around them. But I think the bigger question is what effect do those have on the planetary atmosphere? Obviously, you're interested in this question. And so for LHS 1140, so far, our observations of it indicate that it is relatively inactive in the sense that it has, we don't see strong optical chromospheric emission lines. The star rotates extremely slowly with a rotation period of 130 days, which tells us through Elizabeth Newton's work that it is an inactive star that does not have a lot of high energy radiation. And so in addition to these different thermal environments around that these planets feel around these stars, I think helping us understand the problem of what is it like to be a habitable planet around an M-dwarf star, having a variety of, a knob that we can turn here is really, really helpful. And so it's great that we have TRAPPIST-1 and Proxima, which are sort of on the more active side, and this less active LHS 1140. Yeah, Charles?
So Charles Alcock, CFA. You mentioned Elizabeth Newton's work. Do you have age ranges or estimates for these 3 systems?
So ages for M-dwarfs are extraordinarily difficult to measure. For LHS 1140, from its very long rotation period, matched to galactic kinematics in a statistical sense, this is probably 5 gigayears-ish or older. For Proxima and TRAPPIST-1, Can Mikhail, do you have any better answer to the age for TRAPPIST-1? Yeah.
It's from its kinematics. It seems to be something that's 4, 5, 6 to.
Yeah. So the fact that these stars do not evolve substantially once they reach the main sequence makes it very difficult to determine their ages.
Proxima is a triple system, so you have outcomes
Right.
A and B, and then gives you an age of 5 to 6 gigayears.
Exactly. Yeah. Thank you, Ken. Dimitar?
Just as a follow-up on the question of age, since we are talking about out-of-the-box ideas here, maybe we should push our stellar astronomers colleagues to to really push the old-fashioned techniques of observing uranium and thorium spectral lines and getting kind of the age of the star that way, and hence the planetary system. It's not easy, but hey, none of this is easy, so it's doable in principle. Theoretically, it is.
And for that, so if you can observe radioactive decay in elements of the stars, you can learn about the age. I guess to make those observations, you would want a high-resolution spectrograph on a very big telescope, would be my guess, right? That would be our best opportunity. Yes, Gabor.
Well, as one of those stellar astronomers, I think a slightly easier technique, because a lot of those uranium lines are in the UV, and these stars are not exactly bright in the UV, would be to understand better the way activity declines with age. And we've made some progress on that. So the fact that LHS 1140 is inactive does push me to think it's on the older end. But I think we can learn more about the way M stars of different masses, and it really does make a big difference what mass they are, decline with age. And so now there's a lot more data on their photometric variability, for example. So I think this will progress.
Yeah, absolutely. Yeah, I wholeheartedly agree. Okay, last question in the back, so I don't cut into Aoma's time too much.
Hello, I'm Jim Clark of MIT, and I have a question about this Murph instrument that you were using.
Yes.
It says, I looked up some information quickly, it says it's sensitive to the infrared. What wavelengths does it cover, and does it use photometric filters to bin that data at all?
So we observe from about 700 to 1,000 nanometers in wavelength. These are a perfect combination of the stars get brighter as you go farther to the red, but also detectors become more expensive as you go even farther. So this is the balance right there.